Hey guys, this is Alan with Bothell STEM Coach, and today I'm coming to you with another random video math topic. Today I wanted to talk about the associative, the distributive, and the commutative property, and just in general why we care about those properties. And I'm first going to talk about a new number system though. Or not a new number system, but a different number systems. And I want to just do some observations about what we do with such a number system. So consider the set of integers. It's set of integers is usually described with this z. I don't know why, z. But this represents all the, maybe the counting numbers like 0, 1, 2, 3, etc., right? And with integers or our number systems, we can multiply and we can add. Those are two like pretty fundamental operations that are in this number system. So I want to talk about like one thing we can do is talk about modulo arithmetic. And this is where I take z and I simply say, and I'll use the subscript 3 and say it has three numbers in there, 0, 1, and 2. And I'm going to define how we do addition and multiplication. In fact, what we end up doing is, for any addition, if I want to do a plus b, I do a plus b modulo 3. 3 being this one here. And so let's do some properties of what modulo does. Modulo is the remainder if I were to divide it by 3. So if I did 0 plus 1, that would be 1. It works like normal addition, but let's take a look at like 2 plus 2. 2 plus 2 would normally equal 4, but when I do mod 3 to it, the remainder when I divide 4 by 3, I get 1. Because 4 divided by 3 is 1 with 1 remainder, right? So I can write out a table of all the modulo operations. So 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 1 equals 2, 2 plus 1 would equal 3, 3 modulo 3. The remainder when I take 3 and divide it by 3 is 0, and 2 plus 2 is 1. Okay, and we can do the same with multiplying. 0 times 0 is 0, 0 times 1 is 0, 0 times 2 is 0, then 1 times 1 is 1, 1 times 2 is 2, and then 2 times 2 is 4, but modulo by 3, the remainder when I divide by 3 is I get 1. Okay? So this is sort of the mapping of addition and multiplication onto those numbers. So one thing that's, I don't know if it's very obvious to you, let's do some observations. A lot of this has to do with around 0. Now when I multiply, no matter what combination of numbers I do, I only get 0 when one of the numbers is 0. Like I don't get a 0 anywhere else. And you might think, well, that's obvious. And that is an obvious property from our number system, but that is not true for all number systems, as we'll get into in a minute. The other thing is 2 and 1, when I add them together, I get 0. Here, this doesn't happen, or it happens in the integer space only when I have 2 and like negative 2. We call these additive inverses. Additive inverse. And what that means is when I add them, I get 0. So 2 and 1 are additive inverses. I don't know if that makes sense, because 1 plus 2 and 2 plus 1 result in 0. So this looks like a kind of an interesting number system. You'd be like, okay, so what? Like, they have all the normal things that a normal number system would have. Let's look at Z4. It's the same thing, except now I have the set of numbers 0, 1, 2, and 3. And when I do the operations, I do it modulo 4. Modulo 4 is the remainder when I divide the number by 4. So if I do, let's say 0 plus 0 is 0, 0 plus 1, these are pretty straightforward. 0 plus 2 equals 2. 1 plus 1 is 2. 1. Oh, my bad. I have a 3 in there, so I got to consider the number 3 also. 0 plus 3 is 3. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. But 4 modulo 4 is 0. Okay. Now 2 plus 2, also 4 modulo 4 is 0. 2 plus 3 is 5 modulo 4, and that would give me 1. And then 3 plus 3 is the last one, and that gives me 2. Okay, so let's look at the properties of these. These look pretty straightforward. The numbers are not very tricky. 1 and 3 are additive inverses, and 2 is its own additive inverse. So 1 and 3, additive inverses, because they sum up to 0. And 2 is its own additive inverse. This doesn't happen in our number system. When I add two numbers, a plus b, and that's equal 0, the only way that they could be the same number is if both numbers are 0. So both 0 and 2 are their own additive inverses. That's something different about this number system. That doesn't happen in normal integers. But because of the way the modulo arithmetic works, I get a 0 sometimes. Let's look at multiplication. 0 times anything is 0. And 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. So far, pretty easy. 2 times 2 is 4 modulo 4, which is 0. 2 times 3 is 6, which is that's 2. And then 3 times 3 is 9. The remainder of 9 when I divide by 4 is 1. Okay, this is what I think is super interesting and very different than a normal integer number system. 2 times 2 gives me 0. So remember, one of the properties of math of numbers that we use when we're solving like quadratic equations is the fact that a times b equals 0, a equals 0, or b equals 0. This happens in our number system, our normal integer or real number system. If two numbers product is 0, one of them has to be 0. But not in this number system. See, what happens is 2 times 2 gives me 0. One of them, these numbers are not equal to 0, yet when I multiply together, I get 0. Okay? What else is interesting? Let's see. Multiplicative inverses. We haven't talked about this. Multiplicative inverses are when the number is multiplied by another number and I get 1. So when do I get 1? Well, 1 is its own multiplicative inverse, because 1 times 1 is 1. And 2 and 3 is its own multiplicative inverse, because 3 times 3 also gives me 1. So that's also interesting. Okay. So something kind of breaks down in here. Some properties of, but the most important thing is this one, this concept here, that 2 times 2 gives me 0, even though they're not both 0. Something breaks down in this setup where not all of the properties are working correctly. Not working correctly, but the properties are different than they are with the integer number system. And so it's an interesting observation. It turns out that this always happens whenever this is not a prime number. So if this number is a prime number, then this will never happen. Okay? And it would take some math to prove it. The reason this kind of number system is interesting, or you might ask, why is this useful or anything, is this is tied very, very closely to RSA encryption. So if you don't know, RSA encryption is one way that secure communication is set up between computers. That is to say, like when you enter in a password to a website, Like, how do you send that password and nobody knows what that password is? Like, how can no one could read and figure out all the computers that are along the way that might sniff the data? How do they know? You say, oh, well, it's encrypted. Well, how does the other guy know to decrypt the data? How is it? And the key part is there's a key exchange. There's like a sort of a secret decoder ring that has to be exchanged between the two. But then you have a circular problem. How do you exchange the decoder ring without, someone stealing it? And RSA encryption is the answer to that. There's a public key, there's a private key. I'm probably going to that on another video one day. But suffice it to say is the foundation of that kind of encryption scheme, public-private key, is based on modulo arithmetic, which is why, which is a practical application of this kind of number system. So what I wanted to do was just sort of introduce a different number system that was maybe you've never seen before, and at least has some different properties that you would that don't exist in our own number system. And sometimes it's just interesting on its own, but sometimes that can be applied into a real practical application, which is where advanced math tends to go. It's like these weird types of number systems or geometries, and somehow we get interesting results out of it. So I hope you enjoyed that video. Please leave a comment, like, or subscribe if you enjoyed the video, and I will talk to you next time. Thanks.